stream is going. I clicked record. Let me close my Spotify window. Okay, so we're going to continue on with what we've been doing. Yesterday we discussed the chain rule in its many forms. Today we're going to move on with directional derivatives. Let's look at how the poll's doing. So click the poll. Now, most people are neutral, which is like a very common thing these days. Very few people having not so great mornings. My heart goes out to you. I hope that your day feels better than it started. Oh, and it's Thursday. I should update my little scroller. Okay. So let's do this. Share results. Stop sharing. Close. Put myself into writing mode. Okay, I hear someone's alarm in the background. That's so creepy, I can hear it. I'm just gonna mute you. There you go. There we go. Okay, cool. I got it turned off. Okay, so let's talk about this. So let's zoom in. 300%, there we go. Let's undraw. So one of the things that we had been discussing was that, let's say you have a function, let's say you have a function f of x comma y equals z. Okay, that has two input variables, a single output variable. It's a two variable function. Okay, which means the domain is on the xy plane. So x, y plane, and then here's that dependent variable, the z-axis. Okay, so let's say we choose a point in our domain AB. Okay, so you can evaluate that point and get f of a comma b. And if you want a tangent line at that point, well, you need if you want the tangent line at that point, well, you need another point to take the, so that you get a secant line, and you can take the limit of that secant line, right? So we figured out that there were two ways that we could easily do this. You can move your point away in the x direction, right? So you have a plus h comma b. And then you could evaluate that point, and you would get f of a plus h comma b. And then there's your secant line. Well, what could you do? You could take the limit of that secant line. So let's just put limit as h goes to 0 of f of a plus h comma b minus f of a b all over h. Well, that gives us what we call the partial derivative with respect to x evaluated at a comma b. Why is it with respect to x? Because you moved the, you formed this other point to make the secant line by moving it away in the x direction. And you can do the same thing by moving your point away in the y direction. You can, let's do it in a different color. So you get this other point, a comma b plus h. And you could evaluate it and get f of a comma b plus h. And then you could form your secant line with those 2 points. And what would that give you? Well, that would give you the limit as h goes to 0 of f of a comma b plus h minus f of a b over h, and that would give you the partial derivative with respect to y evaluated at a comma b. Okay, right? So there are these different tangent lines you can form, and one of the things that we talked about is with those two tangent lines you can form the tangent plane, right? So looking on that tangent plane, you start realizing that there are many different ways that you could move away from this point a comma b. And we're going to talk now finally, how do you actually get the derivative in any general direction, not just moving away from the point parallel to the x-axis, not just moving away from the point parallel to the y-axis, but if you want to go in any random direction. So that's what we call directional derivatives. Okay, so hopefully this has sort of like activated your memory about the partial derivatives. Right? The partial derivatives are just, you move away from the point that at which you want your tangent line parallel to the x or y axis. Okay, so let's talk about how can you get the tangent line at AB for z equals f of x, y. How can you get the tangent line with any direction, not just parallel to the x or y axis? Okay, so that's what we're going to be answering here. Okay, so let's come up with some terminology. Okay, so just like I was talking about before, you're going to have a comma b. That's the point in your domain. Okay, so it's a point on the xy plane if you have two variables. Okay, we have our function z equals f of x comma y. It has some surface that you could evaluate by plugging in the points. Okay, so we have to move away from this point a comma b. So h is going to be that distance that the secant, h is the distance that the secant point moves away from your starting point. So h is the distance between your point x comma y and a comma b. So right here we're going to have that point x comma y. Oh my gosh, Burrito, please don't make me take you out right now. He's like looking at me. He's going to start barking. Okay, we're going to pause for a moment because the dog needs to go outside. So just give me a moment. Yeah, he wants me to come out. Okay, we've returned from our bathroom excursion. Hooray. Okay, so back what I was doing. We got this point a comma b, point in the domain. We got this other point x comma y. H is going to be the distance between them. Cool. Which is measured. Okay. Actually, I need to show us a top-down view of this. Okay, so this is going to be the xy plane viewed from above. So this point A comma B, let's say it's like right here. Okay, so hopefully it makes sense to everyone that we're viewing the xy plane from above. Okay, and then let's just say that our other point, that x comma y is going to be right there. Actually, no, let's move it. Let's put it all the way over here, so there's just enough space. So there's your x comma y. And then the distance between them is h. Okay, so we are going to measure there's an angle involved here. And you know how you always, when you measure angles, you start from the positive x-axis and go like that? So you can imagine at a comma b, I would draw something parallel to the x-axis. So do you see how I have it drawn? The x-axis is sort of like quote-unquote, it looks like it's vertical, and the y-axis looks like it's horizontal. So here's my quote-unquote x-axis. And we're going to measure this angle right here, which is going to be theta. Okay? So, when you have an angle theta, you can now talking about moving in the direction of a vector. So I'm going to talk about the vector u, and this vector u is going to have components cosine theta and sine theta. Or you could write it in with the, I forget what the names of the i's and j's are, but the unit vectors, there we go. You can write it as cosine theta I hat plus sine theta j hat. Okay, so this vector u is a unit vector, and it actually is right here. It points in the direction of x comma y, I guess is my whole point. Okay, so u is a unit vector that it starts, the initial point is at a comma b, and it points you in the direction of that other point x comma y. Okay, we needed a vector to tell us in what direction our tangent line was going to be pointed, right? Before, we had our tangent lines parallel to the x-axis, and we had our tangent lines parallel to the y-axis. Now we needed a way to specify any given direction. Did someone have a question? Or did they just get connected? I heard like all of a sudden. Okay, I should pause and see if there are questions. Does it make sense that what this vector u is doing, it's pointing towards the point that's forming the second point for the secant line? And did we get how I came up with that? Yeah, exactly. So my starting point, basically, yes, is over here. My end point is over here. Through my starting point, I drew that red dashed line, which is supposed to be something parallel to the x-axis. Because remember what I was saying is that to measure angles, you always start at the positive x-axis and rotate that way. Okay, no, all of this we're looking, so if we're looking down at the xy plane, so we're forgetting about z right now. Oh, and I guess also what I should point out is that I drew this wrong, slightly. We should actually measure the angle from here. Because we always measure from, like, what would be the positive x direction, and we usually have the positive x direction coming at us. But either way, you have to swing and measure from the x-axis in the direction of the thing you want to go. Are you okay?
Did you eat my ice cream?
No.
Where'd it go?
I don't know, but I'm lecturing. My daughter just came and accused me of eating her ice cream. She was having a bad morning, apparently. She was hoping to eat ice cream for breakfast, but one of her sisters got to it first, as far as I could tell. And she saw it fit to come to me while I'm talking about Calculus 3 to ask if I had eaten her ice cream. Oh my, the joys of being a parent. That was hilarious. Okay, back to talking about this. I don't know if you're able to see, but like, oh yeah, that's how you hide things from your brother. Yeah, they hide so much from each other. It's like so hilarious. Like, I have to do it myself. Like, I feel bad because usually I am the one who eats the ice cream. I'll wake up in the middle of the night and I'll be like, I'm the one who bought it. Like, this is why it's mine to have. I have 3 brothers, nothing is safe. Oh my god. Yeah, everyone knows what it's like to have siblings like that. Okay, so back to this though. Get mini fridges, yes. I probably should just get everyone a mini fridge. And then they each have like a little padlock on it or something for their own little personal ice cream stash or something. But they're not that old, and that'll just be. Also, the problem is the place where we live, they have like the 2-prong outlets, and most mini fridges require the 3-prong outlets. So that's like an issue. But anyways, okay, back to this. Okay, we're looking down at the XY plane. So we're just looking at what's happening in the domain right now. Okay, you have this point AB in the domain, that's your start point. You have a point XY in the domain, that's your end point. If you draw a line between them, you want a vector that would point from your starting point to your ending point. What I'm saying is that if you can measure that angle, so the way you find that angle is by drawing this like imaginary x-axis. It's something that's parallel to the actual x-axis, and then measuring from that line, the angle, to the other line, which points in the direction you want, that can form the vector. Okay. So, what we're going to use this to do is now we're going to write that ending point, x comma y. We're going to write x comma y in terms of the starting point a comma b, the distance traveled h, and the vector u. Okay, so this point, let's talk about the x coordinate of that point. So we're going to start at AB. And then what are we going to do? We're going to travel a distance h according to the angle cosine theta. Well, what about the y value of that point? Well, we're going to start at the starting point B, and we're going to travel a distance h in that direction. So this is that point right here. So by setting h, we can now slowly move in this point as we take the limit to turn the secant line into a tangent line. Okay, so let's define this secant line. We have our a comma b. That's in the domain. You evaluate it, and you get f of a comma b. Yay. Now we have our second point. It's over here. Our second point is a plus h cosine theta, comma b plus h sine theta. Okay, so what we did is we traveled in the direction of that vector u a distance of h away. And we can evaluate that point and get f of a plus h cosine theta, comma b plus h sine theta. And using those 2 points, we can form our secant line. So what is our secant line, or the slope of our secant line? Well, you're going to have the difference of the z values over the difference, or the distance between the 2 points. So that's going to be f of a plus h cosine theta, comma b plus h sine theta minus f of AB all over the distance between the 2 points, which is h. This should look sort of familiar to the secant lines that we made earlier for the x and y partial derivative, but notice you're making changes in both the x and the y direction. Remember how before it was just like f of a plus h comma f of b, or sorry, f of a plus h comma b minus f of a comma b for the x one, and then the other one was just f of a comma b plus h minus f of ab over h, right? Because those only went in one direction. Now you have to add h into both of them, right? Because you're traveling in an arbitrary direction. So this is the secant line for that arbitrary direction. Thank you. Wow, having difficulty. Now I'm going to pause. There are probably questions. We will see. It's hard to say. Does it at least make sense that this is no longer just moving away? You're no the secant line isn't just moving away from your point in the x or y direction. It's moving in some arbitrary direction. How do we feel about that? Does that make sense or no? Okay, cool. Okay, so how are we going to make this directional derivative? Well, we're going to take the limit of this secant line. So we have some special notation for this. We talk about the directional derivative in the direction of u. Oh, yeah, I will pause. That actually just makes my life easier because I can go and quickly make some toast while you write it down. So thank you for asking. You're gonna walk away. Allow you to write and get some toast.
What?
See you on Discord all the time. Gotta keep those bad vibes out of my bed. Oh my god, you're spilling. Your thing's spilling. Oh, after you eat, can you please do a little one?
Okay.
You didn't do one last night.
Yeah. Are those clean?
Yeah.
What's clean? Oh, there's sugar.
Did you eat my ice cream?
No.
Who's Daphne? That little slut.
No, Lotus.
My phone is on.
What?
Being broadcast. The microphone is on. Being broadcast to YouTube.
Lotus, what the hell's wrong with you? Don't do that. Say that.
You
Hey,
could
what
have
is-
turned the microphone off, Dad. They don't need to hear you making toast.
Yeah.
I'm just gonna have a nice movie.
You lied to them. You
Or
lied
do you want
to
it?
What?
I was like him today.
Looks nice.
Yeah, I like it.
You.
I like it! Okay, just a little flat on the top, that's all I'm saying.
Yeah,
And it looks nice, it looks nice.
Your hair looks flat right here.
That's how it's supposed to be. You think it should bulge out like that?
Yes. I don't know why, but my hair always does that. It was, as a child, when my hair wasn't like for some reason this wavy, it would just like be like a bob kind of that curled in. But in the back, it would just do this. It would
Wait,
just
for me
so
though,
weird.
one side would curve in, the other side would curve out.
I don't know, but for me, it would just both would curve in, and the back would really just curve out. So it was so weird.
Wow.
In the back, it would.
People would point out all the time.
Yeah, you'd be like, "What the hell's wrong with your hair?"
What? I don't know.
I was like, "What?" And when I first felt it, I was like, "Oh my god!"
Alright, I don't know if you're able to hear them very well, but ha 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 ha, that was very fun. My toast will be ready soon. Very much. Oh my god. Yes. You heard my daughter talking about the other daughter and the accusations made about the eating of the ice cream. Very, very saucy conversation. Okay, can I move away from here? Alright, cool. So whenever we're talking about a directional derivative, we usually use this big D. And then what you're going to put underneath is the direction in which you are moving as a vector.
Ew.
So you put the direction. It was cookies and cream ice cream. Oh man, I had some really good ice cream recently.
Mine?
No. I'm talking about the Earl Grey ice cream that I've been buying. I'm a huge fan of Earl Grey tea. So it's basically like having Earl Grey milk tea in ice cream form.
Super creamy.
It is so good. Yeah, I know, for a simple flavor. Basically, someone's judging you, Lotus, like that, you know, cookies and cream is not worth your angry response.
I was saving it for a friend.
Oh, she was saving it for...
You're mean, Dad. You're selfish.
Oh my gosh. Where do you get the Earl Grey ice cream? I've been getting it at Smart and Final. They happen to have it. I think they also have it at Safeway now. It's a brand called like Van Leeuwen or something like that. They started off as like a internet-only ice cream company. Boba's with a fight. And then you'd have to like have them mail the ice cream to you. It was really good. But now they just sell it in some stores. It's a little pricey. It's like $7 for like one of those little pints or whatever. Or, yeah, I think it's a pint, not a quart. But it tastes good. You know, ice cream being worth it. Yeah, ice cream is just not as amazing as boba, I'll be honest. So you've got this directional derivative. You're taking the derivative in the direction of this vector u. So you always have to specify the direction right under there. And then you have to say, well, this one's going to be the function. So you're going to take the derivative of this function. And then, you know, it should make sense. You specify at what point you're going to be taking the derivative. Okay. So how do you get the directional derivative of f at a comma b in the direction of u? Well, all you need to do is take the limit as h goes to 0 of that thing we were just dealing with, the slope of the secant line. So f of a plus h cosine theta, comma, b plus h sine theta, all over h. Oh, shit. I forgot minus f of ab. Crap, and now my h is not in the middle. Whatever. No big deal. Part of me dies a little, though. Okay, so remember that direction derivative u is defined to be cosine theta, comma, sine theta. And how did we come up with that? Well, you basically imagined that this is your xy plane. Okay, and you had that starting point, a comma b. You had that ending point, x comma y. And you wanted to figure out the direction from one to the other. Well, what did you do? You imagine a line parallel to the x-axis moving through there, and then you measure that angle theta. Because that's how you form that derivative. I'm sorry, directional vector. Oh my god, it's so hard to say these things sometimes. So, guess what we're gonna do now? So fun. Now that we have the definition for how to find these directional derivatives, what do you think that we are going to do? Yeah, so we're gonna compute and find the slope of the tangent line in a particular direction using the definition. So, like, do you remember how, like, in 101A, Calc 1, you, like, calculated the slopes of tangent lines using the limit definition of the vector? That's what we're going to do here. It's so fun. So fun. I mean, it actually is sort of fun. It's just long, tedious, to be honest. Okay, so we're going to do this. Hey, Lotus, could you, like, butter my toast for me?
Will you buy me more ice cream?
Of course.
Okay.
There we go. Bribery always works.
Oh, your toast.
Yeah, my toast is, like, not with me. That's why I'm asking you to do it. She, like, literally walked over here to, like, get my toast from me that I asked her to butter. Okay. So... Oh my god. Let's let our function f of x comma y be equal to x squared minus xy plus 3y squared. So here's our function. And we are going to find the directional derivative in the direction of u, not at a particular point, but for any point x comma y. So, well, what does that mean? It means that here's going to be our starting point x comma y. We're not going to call it a comma b. And our ending point is going to be over here, which, according to the formula, is going to be x plus h cosine theta, comma, y plus h sine theta. Okay, so we're going from this one to that one. Oh shit, my bad. Okay, let me scroll down. Is that better? Okay, cool, thank you. Okay. And we are going to specify... So, oh yeah. So remember how you're supposed to draw the line parallel to the xy axis? And then you have your angle. We are going to specify that that angle is equal to... Oh, thank you. The cosine inverse of 3/5. Okay, so let's calculate this thing. We first need to come up with what our u is. Alright, so remember that our u is going to have components cosine theta, sine theta. Now obviously, since theta equals cosine inverse of 3/5, what do we know that this one's going to be equal to? Let's see if people are paying attention. Our angle is equal to cosine inverse. Right. The cosine of cosine inverse of 3/5 will just be 3/5. Very good, thank you. Now, we need to figure out what the sine of this angle will be. You could just use a trig identity. We know that the sine, well, here. We know that cosine squared theta plus sine squared theta equals 1, right? Our cosine is 3/5, so cosine squared will be 9/5. So we know that sine squared theta will be equal to 1 minus 9/5. I'm sorry, 9/25. I only squared the 3, not the 5. So you can take the square root of both sides. And you get that the sine of theta is equal to 25 over 25. 25 minus 9 is 16. Square root of 16 over 25, 4/5. So this means that we're doing the directional derivative in the direction 3/5, 4/5 of f at the point x comma y. Does it make sense? We can like plug in that value u now. If you want to, you can write that as opposed to just u, now that we know what u is. Okay. And now we can start like calculating it. So this directional derivative in the direction 3/5, comma 4/5 of f of x comma y is going to be equal to the limit as h goes to 0 of, okay, so we're going to have f of x plus, like what I wrote earlier, h cosine theta, comma, y plus h sine theta, minus f of x comma y, all over h. Okay, so now we're going to need to like actually start plugging that into the function. So I'm going to copy down our function definition here. Okay, wait, I didn't want to. I want to copy it, not move it. So I'm going to paste it here so that we can look at it. Okay, so what we're going to have to do is, let's just simplify this. Or work on this. We're going to work on just this part. Copy. Paste. Okay, fill in the parts that it didn't get. Okay, so what are we going to do? We're going to take our x component and we're going to square it. So we're going to get x plus h cosine theta quantity squared minus the x component, so x plus h cosine theta, times the y component, so y plus h sine theta, plus 3 times the y component squared, so 3 times y plus h sine theta quantity squared. Okay, does it make sense how I'm doing that? I'm just calculating this part up here right now. Right, do you remember doing this from the limit definition in like 101a? You'd have to do like f of x plus delta x minus f of x. It's just way more complicated because there's like way more stuff going on. Okay, so let's start multiplying. We're going to get x squared plus 2x h cosine theta plus h squared cosine squared theta minus, and then in parentheses let's distribute x y plus x h sine theta plus y h cosine theta plus h squared cosine theta sine theta plus 3 times, that one's squared, so y squared plus 2y h sine theta plus, holy crap, so long, h squared sine squared theta. Oh my god! That was a lot. some stuff hopefully cancels. Oof. I'm like looking around to figure out like what exactly is gonna cancel. Holy crap, does like anything cancel? There are so many terms. Holy crap. Okay, one second. I'm like looking through here. Okay, yeah, we're good so far. Just want to make sure I didn't make a mistake. Okay, that one's good. Oh, okay. I guess we get some that actually do cancel. There's very few though. Okay, what could you do with these two? Your h squared cosine squared theta and h squared sine squared theta. Yeah, so you'll factor out the h squared, the cosine squared plus sine squared will be 1, right? And that will just give you h. Other than that, okay, I'm like going through and trying to figure out what else will cancel. So like bear with me. Okay, let's just rewrite them. Factor out the 2x of the 2yh sine theta. Factor out the 2x of the 2... I'm trying to find like where that is. Well, I guess let's go and talk about the things that definitely aren't going to cancel. The x squared, nothing happens there. Okay, so what should I probably put next to it? The 3y squared. Okay, and let's just write a line through it. Done with that. Okay, then we've got 2xh cosine theta. Are there any other xh terms anywhere? I guess you've got these. That's an xh term. Okay. Yeah, okay, so those go to... Actually, yeah, those would go together, right? You could factor out the... You could say plus 2 cosine theta minus sine theta and then xh. Does everyone agree I could do that for those two terms? They both share an xh in common. There's nothing else with an xh. Did I actually multiply this out right? xy, xh sine theta, h. Oh, did I? yh cosine theta. Okay, cool. Yeah, I did that one right. H squared cosine theta sine theta. Okay. Oof. Okay, so we'll just say that those are good. Okay. We'll provisionally put a line through them. I guess we've got this minus xy. There's nothing that's really going to happen with that. Or I guess it would have been nice to put it over here on the left, but whatever. Okay, let's look at this term. You have a yh. Are there any other yh terms? Yeah, there's a yh term right there. So you could put plus you'd have to distribute the 3, and you would get 6 sine theta minus cosine theta YH. Oh, I see what's going to happen. Okay, cool. So then that one's done, and then that one's done. Okay, and then we already dealt with those h squared terms. And that would be those. Okay, then you have this one. So plus h squared cosine theta sine theta. Oh, okay. Now, what do we know about cosine theta and sine theta? Like, what are they equal to? Like, I completely forgot about this. No wonder I was, like, drawing a blank. Like, what do we know that cosine theta and sine theta are equal to? No. Each of them individually, not when squared and added together. I'm going to scroll up. What do we know? They're what? Yes. Or 4/5, right? They're equal to 3/5 and 4/5. So you can make those replacements. So let's make those replacements. I'm going to write x squared minus xy plus 3y squared, because those are the things without those. So what does this term become? We're going to get 2 times 3/5 minus 4/5. So that's going to be 6/5 minus 4/5, which is going to be plus 2/5 xh. Okay, and then you're going to look at this term. Well, you're going to get 6 times 4/5. It's going to be 24/5 minus 3/5. That's going to be equal to 21/5 YH. Okay, and then what's this one? That's going to be 3/5 times 4/5, which is 12/25. So you're going to have H plus 12/25 H. Holy shit, what's 25 plus 12? 37. Yeah, thank you. 37/25 H squared. Okay, I think I did the arithmetic right. I'm not sure though. Okay, that's matching. That's matching. I seem to have fucked up the 37/25 though. Supposedly I'm supposed to get 9/5 there. What did I fuck up? Okay, everything is right, but I know that I have made a mistake with this number. Which means I made a mistake over here, at least. Does that make sense? I'm pausing because everything is good up to there, except for that one number, because I'm like looking at what I'm supposed to get, and I'm like wondering where I made my arithmetic error. Shit, what did I do wrong? Oh, I see what I did wrong. Okay. this is supposed to be h squared, it's supposed to be 3h squared sine squared theta. And what was sine squared? 4/5 squared is 16/5. So I'm supposed to have 3 times 16 25ths. Okay, yeah. Okay, wait, okay. I must have some other mistake somewhere else. Okay, erase. There's some problem here. Okay, so. Oh! Okay. No. What the hell? Oh. Okay. That's supposed to be h squared times cosine squared. Cosine squared is 9 25ths. And then it's supposed to be 3h squared times sine squared, which is 16 25ths. And then for that one, we're supposed to have h squared cosine times sine, which is the 12 25ths. Okay, now if you add all those together, you're going to get 9 plus 3 times 16 is 48, plus 12, 50, 60, 69. 69 25ths. Is that correct? No, it's not. Okay, do you know what? I think because of coronavirus, I'm allowed to throw in the towel. I screwed something up. I'm gonna have to go and look at this and figure out where my mistake was made. I have one number that's